Good afternoon, everybody. So today is October 26th, our 20th class of the semester. And I have to tell you up front, I've had internet issues here at home today. Usually it's, well, in the past, it had been more consistent here at home than it is on campus, but this semester has been one problem after another. Spectrum was out for a while earlier, and then the power flickered too. So we have underground utilities here in this subdivision, and I don't know if this is the case or not, but I think when Optics put in their fiber cable over the summer, I think they damaged some of the existing infrastructure that was there. They used a boring machine. And yesterday, when I was coming home from campus, I noticed that there was a big orange cable going from one utility box to another. And I think that there's some problems with the underground cables now. But I don't know if it's really Optics' fault or not, but since COVID 2020, we'd had outstanding service. And then when the Optics network came in, our service with Spectrum has declined quite a bit. Anyways, let me jump in with some announcements here. Office hours this afternoon, 2:30 to 4. So if you guys need to meet with me about anything, just jump in my virtual office hours about an hour after class. Give me a little bit of time to catch my breath and get a drink or something to eat. Here's our due dates. So I've got 3 homeworks posted, 7, 8, and 9. I went through and graded another one yesterday. Again, I urge you to double check your solution against mine. I look through the things that you submit to make sure that you're putting in the effort, but I don't always check the numbers. So I'll continue to catch up on grading of other homeworks as time permits. It is going to be a take-home exam the week of the 13th. We've got 1, 2, 3, 4, 5, 6 of the 7 of you. So the 7th person, I'll make sure I reach out to him and make sure he knows about that, because I think he's behind in the class, and I'd hate for him to miss that announcement. All right, so today on our agenda is to wrap up some loose ends from Tuesday's lecture, where we were talking about 3D frame modeling in SAP 2000. Then I want to jump back over and go through another presentation, this time talking about continuum elements in SAP 2000. And that's going to give us most of the vocabulary that we need in order to work in ETABS. And so let me do that. I'm going to jump over to my other workstation now. I need to give me permission to share. Oops, that's there. And okay, hopefully you can see my SAP 2000 screen. Yeah, okay, good. All right, so at the end of lecture on Tuesday, I was moving from 2-dimensional models into a 3-dimensional frame, and I was using the replicate command quite a bit. And I had used it erroneously, or in one case, and copied the girders in the wrong direction. So I went back through and I fixed that. So what you can see here on the left is a fixed model, a repaired model, a correct model. I still don't have the right member sizes in there, but for the purposes that I want to use it for, it's going to work just fine. I did a couple of other things to it as well. One of the things that was missing from the model was I didn't have the gravity framing properly restrained at the bases. And I went back and I added that. And then I went in and I deleted the joint constraint definitions that I had as well. And I want to reapply those after I show you a couple of things. One of the things that I tried to do during lecture on Tuesday, not successfully, was that I was trying to define groups to aid in our manipulation of the model. So a couple of things here. Over here on the right-hand window, I'm showing a two-dimensional view. And if you look at the tab up here, it tells me where I'm at. I'm looking at the XZ plane at Y equals 0. And if I click in that, you can see in the left-hand plane, there's a little pale blue box that indicates which of those frames that I'm looking at. So that kind of helps orient you within the 3D model of which 2D version you're looking at. Now, I think you guys probably picked up on this, but it's easy to change from one view to another. If I want to look at the brace frame, for example, I can go to a YZ view. That's going to give me the brace frame in frame line 4. I could click over here. That's going to give me the brace frame in frame line 1, right? And so that is pretty nice. In all cases, though, I'm looking at a three-dimensional view here. I'm sorry, two-dimensional view. So there's no way to pan around and look at the way any of the members are oriented or anything like that. So another thing that you guys probably noticed that I did was I can go over here to the left window where I have a 3D view defined, and I can set limits. And if you're conversant in Autodesk Revit, then there's a window box you can use in Revit to limit what it is you're looking at. And this is very similar to that. And so what I can do is set my bounds. If I want to limit things in the one plane or another, let's see, if I want, I'm looking at the XY plane now. So if I want to look at just one frame in the XY plane, I can draw a window over that. I hit apply. And now I'm looking at the moment frame in framing line D. Now I can get the same thing over here in this window on the right. So let me do that. Let's go back here, define a 2D view. I'm going to look at the XZ plane at Y equals 72. And so I'm looking at the same frame in both views, but one thing that's important to note is this is a 2D view on the right, whereas this is a 3D view over here on the left. And so I can pan around on this and manipulate it any way that I want to, because it's portrayed or depicted as a three-dimensional view. And so now I could go in if I wanted to and look at the extrude view of the model. And then I can zoom in and look at the way the members are oriented and that sort of thing. So you can see how the beams and the columns are arranged, right? All right, so the those view options are fairly dynamic. There's a lot of good tools that are built into SAP 2000, but I would be lying if I said that the graphics are awesome, right? If you go and look at something like Autodesk Revit or Autodesk Fusion 360, the graphics and the renderings that are available in those packages are just far superior. I hope that someday in the future that SAP 2000 will just go ahead and rebuild their GUI from the ground up so we get better renderings, but you know, their focus is appropriately on analytical tools, not necessarily graphics tools. So that's, yeah, one of the drawbacks. And you guys saw with Maggie last week that if you look at Tekla Structural Designer, TSD, that the graphics there are, at least in my opinion, better. And I suspect that that has a lot to do with the idea that TSD is a younger piece of software. So when it was written, the graphics tools that were available were superior to what's built into SAP 2000. Let me go in here and get rid of the extrude view. I think I just did that. Nope, I did not. There we go. Now hit apply. Let me do one more thing over here. I want to go back and get rid of the window box or the limits. And so there's a button here. I can show all Y, show all X, hit apply. And then now I get the entire model back. All right, I've got the releases shown in there. They kind of make the window a little bit cluttered. So let me get rid of those as well. Okay, good. I can even get rid of the nodes, make them invisible, and then that makes the window even less cluttered. There we go. Okay, so one of the things that I was trying to do the other day was to name groups, and I was just, I wasn't able to get it to work. I think I had the right process, but I didn't execute it properly. I went back and tried it again after class, and it worked just fine. And so the process is 2 steps. One, you go in and define what you want the groups to be. And I have 4 groups defined plus the default all. And so basically I have one group for moment frame one, another for moment frame two, brace frame one, brace frame two. And so what I did is you define what the groups are. Then the second step is to select something, members or nodes or something like that. Then you go to the assign and you assign those objects to the groups. And so it's a two-step process, much like it is defining a joint constraint. And so the benefit to that is that you can isolate those things more easily than you would be able to without. So for example, if I want to just look at the moment frames in this view on the left, I can go in here and say select, and then I can select using groups, and I can select all the objects that are assigned to the two moment frame groups that I defined before class. I hit close. Now what I can do is go over here to the view window and I can show just the objects that are selected. And so now I'm looking at a 3D model that has all of the beams, columns, and braces in it, but I'm only looking at the beams and the columns that are part of the moment frame groups. And so that could be really useful when we're looking at the results afterwards, because now I can go in and analyze just the moment frames and the view isn't cluttered by everything else. So let me go ahead now. I'm going to go back to view. I want to show all. Let me show you how I would do the assignment for the two brace frames. So I need to remind myself what the framing layout is. So off screen here, I have the PowerPoint that we've been working from. So I've got brace frame one is in framing line one, brace frame two is in framing line four. I should have a better naming system, but I don't. So let me go over here in my 2D view. I'm going to define that 2D view. I want to look at the XY plane at X equal, I want to look at the YZ plane at X equals 0, which is framing line number one. And so that brings up this 2D view on the right. I can go in here now, window over the members that make up the braced frame. Now I can go to the assign menu, go to assign to group. I want those to be a part of braced frame number one. Okay, let me close that. Over here on the right, I'm going to switch over to the the YZ plane at X equals 96 feet. And that gives me brace frame in framing line number four. And then I'll do the same thing. I'll window over that brace frame. Now I'll go to assign to group, and then I'll assign those objects to brace frame number two. Hit apply, hit close. I'll close this window out as well. Now what I can do over here is I can select based on groups. There it is. And now I can select all four of those lateral frames, select those. Then I can go to my view menu and I can just show the selected objects. So now all you see are the lateral frames that are part of that model. Now, the rest of the framing that's in the model is gravity framing. So what I can do then is I can go over here to the select. I can invert the selection. Invert selection. And so that basically selects everything that's not part of those groups. And so there's nothing in the view on the left to see that was selected. But if you look over here on the right, it selected the remaining members that were. So now I'm going to go in and assign those to a group. I'm going to go to my group definitions. I'm going to add a new group. I'm going to call it gravity framing. If I can spell it right. That's a lot. Nope, I still spelled it wrong. Okay, and I'll go ahead and hit OK. I'll hit OK again. Now I'll go over here and I'll add those members to that group. Hit close. Now I can go over here. I can go to select by group. I can select the gravity framing. Even though it's not shown in the window on the left, it's still selected. And now I can go here to view and show selection only. And now I get the gravity frame. And so what you can see is that we're missing pieces of the model, and everything that's missing is something that's been assigned to the lateral framing groups instead. So I was trying to show that on the fly on Tuesday, and I hadn't rehearsed it beforehand, so I must have screwed up the order of operations or something along that line. So, all right, let me go ahead and show all. So that's Control Shift A. There we go. Now the entire model is back in here. So I told you the other day, or I told you that after I finished class the other day, I removed the joint constraint definitions that I had. So one of the things you'll see here is that I don't have any joint constraints. And to illustrate the idea of the importance of a joint constraint, what I'm going to do is I'm going to put a couple of loads in here. I'm going to go ahead and just select these two nodes on that face there. So I'll hit Shift and select that one. Come on. There we go. And I'm going to go ahead and apply a load there. That's going to be in the X direction. So I'm going to go in here. I'm going to assign joint loads, forces, and let me go ahead and add it to, I should create a new wind load, but let me do that. Define load patterns. Let's call it W, and I'll call it point loads because it's going to be point loads. It's going to be wind like that, and I'll add that in. Hit OK. Now, if I go in, I can assign joint loads there. Let me just make up a large number. It's going to be in the X direction. Let me put 100 kips at both nodes. I hit Apply. I hit Close. Now, let me define my limits, and I just want to look at the first story of framing. So let me look at the XZ plane here, and I'm just going to window over that, which gives me my first story of framing. There we go. Okay, now if I go in and run this model, I can go in and look at the display shape that I have under that wind load. So let me go in here, select W point, hit Apply, and let's close this window out, and we'll animate that. I love the noise. All right, now, so you see the problem that we have without the diaphragm defined in this model is that the loads where they're applied at this edge aren't transferred over very well to the moment resisting frames that are on framing lines A and D. And there's a little bit of transfer of force over there through some frame action that exists in the model. But what we would expect to see instead is that thing shift as a plate element or as a diaphragm. And so what I want to do now is go back in and define diaphragm constraints and show you the difference in behavior that occurs when I do that. Let me go here on the right. I'm going to define a separate 3D model. Let me get rid of those joint restraints or member releases instead, rather. There we go. Now I'm going to do this. I'm going to orient this model so that I can select a lot of nodes. Let me go in and let me define the constraint first. Joint constraints. I want it to be a diaphragm constraint. Add that. And it's going to be Z-axis, and we'll say we want a different at each Z level. Hit OK. Hit OK again. Now what I'm going to do is I'm going to select all of the nodes, but I'm not going to select the nodes at the ground level. I did that the other day, and I think that led to numerical problems where we have a constraint assigned to nodes that were also restrained. And so if you assign a constraint and a restraint to the same node, you're basically over defining its degrees of freedom. So let me go here now to assign joint constraints, and I'll assign the diaphragm constraint to all of those nodes. Okay, I'll close that out. I'll close this out as well. Let me go in and redo the analysis. And now let's look at the deformations that we get out of those wind loads. So looking over here on the left, now you can see how that translates as a rigid diaphragm instead of having the frame action and giving us the in-plane deformations that we don't want. All right. So at this point, then the last step would be to go in and define our loads a little bit more explicitly. So let me show how I would do that. Let me unlock the model. Thank you. I can use this model here. I'm holding down the shift key and then the center mouse button in order to pan around. And yeah, the graphics are getting a little wonky, for lack of a better word. I think that when I'm using Zoom to capture the screen and I'm using SAP 2000, I don't think those two packages play very well together. There we go. Now refresh that. So what I want to do is I'm going to go in and define my load patterns again. And the other day when I had diaphragm loads, I had them, the loads in the X and the Y direction defined in the same load pattern, which makes it impossible to decouple them. It's impossible then to apply the loads in the X direction without the loads in the Y, or vice versa. So I'm going to go ahead and delete that load pattern. I'm going to create two new ones. I'm going to call it WX for wind with a user-defined wind pattern. Let's see, add new load pattern. I'm going to call this W sub Y with a user-defined load pattern. There we go. And so what I'm going to do next is go in to my model, and I'm going to define the wind loads that I want to apply to this structure. So here's our wind criteria. We want to apply the wind loads that result from a 115 mile per hour base wind velocity with an eccentricity of 15%. And so what I'm going to do is basically take these loads here, 23.7. That's going to be the force that I apply, but I also need an in-plane moment as well. So if I go in and multiply that force of 23.7 kips times 15% of the breadth of the building, 15% of 72 feet, then what I end up with is an in-plane moment of 256.1 kip feet. So I'm going to take these values here, W sub XD and W sub X moment. That's the wind in the X direction that's directly applied as a force and the moment that results from that. And I'm going to define those in the wind load definitions for the diaphragms. So I can go now to define, go back to load patterns. I can go to my WX case, and I can go to modify lateral load pattern. And so what I'm doing then is just typing those forces in, 23.7, and then the moment that I have that goes along with that is 256.1. And so I got to make sure I'm in the right units because I've got kips and feet, and that works out just fine. I put that in the wrong box, so let me fix that. That should be FX, 23.7. Okay, down here I have 26.2, and then 282.8. Right, and you basically can enter in your story forces like this, and I find it to be a lot easier than applying loads to the outside of the building. Okay, I got the wrong number again. I just talk about how much easier it is, and then I screwed up. 266.2 here. Right. And so we could go through and do that for all of these 23.7. Let me do it this way. 22.6, 21.1, and 19.5. This here is going to be 256.0. This is 243.8. This is 228.3 and 211.1. Okay, I'll save you the agony of watching me put those in the other direction. Let me delete those point loads. Don't need that anymore. Hit OK. Now I can go through and do my analysis. All right, and so what I can, oh no, I got an unstable.
Welcome back.
Ah, good. There we go. I was worried everybody else left. Yep, that's Spectrum for you. All right, let me get back in here. So I'm on my Verizon phone right now. I have 5G service, but in order to make it work, I have to perch it in the window. Okay, pardon the interruption. I wonder if that'll come out as one recording or two. Find out, I suppose. All right, so yeah, over here on the right, I'm going to select the XZ plane again. Let's look at the moment frame on framing line A, I think it is. And so there we go. Now what I can do is come in and look at the moment diagrams over here on the right. So I can go to frames, look at Win WX. I can look at the bending moments that I have. And I get bending moments in the members that I would expect, and I get not bending moments in the members that are supposed to be pinned. So none of the gravity beams have any bending moments in them, but the columns over here on the corners, those are gravity columns. They still have some bending moment in them, though, but it's small. And the reason there is bending moment in those columns is because those columns are continuous across the floor levels. We don't pin them at each end. If you can do that, and it's not irrational to pin them in the model, but when you do that, then you run the risk of getting some instabilities in the model that would create problems for you. If you release it too much, then you'll start to get warnings out of the software that aren't great. Then we can go over here and look at displacements in the 3 dimensions. So we can go to WXY, hit apply, and we can animate that. Right. And if we go in and look at the 3D view from the top, let's see, I'm better off doing this. Stop that. And then hopefully from this direction, you'll be able to see translation and a little bit of rotation. I don't see the rotation, but it's there. All right, so that gives us a lot of tools to work with. We're still missing a few things in this model, though. Most notably, I haven't applied any of the gravity loads. I haven't applied the snow load to the roof, the dead load to the members, the curtain wall load. I haven't applied the live loads or anything like that. And the reason I haven't taken the time to do that is, number one, I don't want to bore you guys any more than I already have in class. But second, there's a really easy way of doing that if we use shell elements. And the problem is that we don't yet know what shell elements are. So let me go ahead and shift gears to our presentation on continuum elements. Let's see, I gotta find that. There we go. All right. And so the first thing we want to do is define what a continuum element is. So what we've been doing so far is using discrete element modeling, where we basically use one element or one object to model every physical object that's in our structure. Now, it's not strictly true when you talk about automatically meshing beams into 8 sub-elements or 10 sub-elements, then we're not really using one element for every physical object in the model, but I think that that's still a fairly good definition. On the contrast, finite element modeling is where we use several elements to model each physical object within our model. And in the most common type of element that we're using in that case is a continuum element. Beams and frames and trusses, those are line objects. They only have one, let's see, one dimension that defines them, and then you apply section properties to them. So when you look at the definition of a line object, it has a length. Then you assign section properties to it, but in our model, it doesn't necessarily have a height or a breadth. Continuum elements, on the other hand, usually have at least two dimensions that define their geometry, either a length and a width, sometimes also a depth if it's a three-dimensional object. So the type of continuum elements that are available in general are plane stress or plane strain elements, plate elements, shell elements, solid elements, and then axisymmetric elements. So an axisymmetric element is an interesting element that we don't use very often. But if you have a structure that has an axis of symmetry, then you can use an axisymmetric element to model that. And so a common example that I use is if you had like a cooling tower on a power plant like this, for example, then you would have an axis of symmetry that goes down through the center of that cooling plant like that. And so what you could do then is define an element that is axisymmetric, and you could model the behavior of that cooling tower by just defining a section. And then the model, when it does its analysis, takes that section, revolves it around the axis that you define, and so you can have an economy in your analysis by using that axisymmetric. What we're going to use most often in our class are the shell elements. If you go into more advanced finite element modeling, some of the graduate level courses, then we use solid elements quite a bit in programs like Abacus or ANSYS to do modeling of components and things like that. In this class, so the shell elements are very useful for us to model planar objects like a floor slab, like a bridge deck, like a shear wall, things of that nature. And so that's where we're really heading with this. The rest of the stuff isn't uninteresting, but for the purposes of this class, we need to know what shell elements are in order to be able to use them in our models. All right, so let's define these elements. The plane stress and plane strain elements come in a couple of different flavors. There's a triangular element that has 3 nodes and a quadrilateral element that has 4 nodes. It looks like a square, but it doesn't have to be square. It just has to have 4 sides. So that's why we call it a quadrilateral element. And so when you go and look at this, the 3-node triangle has 3 nodes defined, defining its geometry. So J1, J2, J3, joint 1, joint 2, joint 3. And then we have the local axes here, axis 1, local axis, axis 2, and then the local 3 axis is perpendicular to the plane that's defined by those three nodes. And then at each one of those nodes, we identify 2 degrees of freedom. So this element has a total of 6 degrees of freedom associated with it, 2 degrees of freedom at each node. And so one of the limitations is that it doesn't permit any out-of-plane deformation. It doesn't permit any bending either. It's totally a plane element. The one on the left is very similar to the one on the right. The quadrilateral is similar to the triangle, with the exception that we have a 4th node that's defined. And along with that comes 2 more degrees of freedom, degree of freedom 7 and 8, as I've shown here. All right, now when we look at the output that's associated with these, we usually look at the stresses that are in the local directions. So we have the 1 axis here, so we have a sigma in the 1 direction, sigma 1, 1. We have the 2 axis here, so we have a sigma in the 2 directions, sigma 2, 2. And those are normal stresses. And then there's also a shear stress as well. And on this face here, we'll define it as sigma 1, 2. And that's really a shear stress. But if you go back and look at it from a fundamental point of view, a lot of the older texts don't distinguish between sigma and tau for the shear stress. They just use the notation sigma 1, 2 as a shear. So if it's a sigma 1, 1, it's a normal stress. Sigma 2, 2 is a normal stress. Sigma 1, 2 is a shear stress. And so the notation there is that that's sigma on the 1 face, but acting in the 2 directions. So That's, I think, how that works out with that notation. And that's something that might vary from one package to another. All right, so when we look at plane stress elements, by definition, the stress in the perpendicular direction, the 3 direction here, is going to be equal to 0. When we look at plane strain elements, then the strain in the 3 dimension is equal to 0 instead. And so at first thought, you might think that the two are equal, but they are not. If you have a plane stress, that means that the outer surfaces of your element are free to move in and out. So if you take a plane stress element and you pull it, it's going to get a little bit thinner because of Poisson's effects. But the stress is always equal to 0, even if the strain in the 3 dimension is not. On the other hand, if you look at a plane strain element, then the strain is taken as equal to 0. So if you pull on it in one direction, it doesn't get any thinner, but instead it develops a stress corresponding to the restraint that you apply in that 3 direction. So most often we're looking at plane stress elements that are useful to us. If you were going to model, say, a plate to represent the flange of a beam, most often you would use a plane stress type of an element. But if there are cases where a plane strain element is appropriate, and if you were going to model a gravity dam, for example, a weir, then you would probably take a slice of that dam and model that section. And because that dam is generally much longer than the sectional dimensions, you would probably choose to model that with a plane strain element instead, because that dam, being as long as it would be, isn't free to contract or expand along its length. Okay, when we look at plane stress elements compared to a plate element, you can see over here on the right, we have different degrees of freedom defined. First of all, the plane stress element doesn't have anything going on out of plane, right? So we have forces that are in the plane of the element. Whereas with a plate element, everything is out of plane. We have an out of plane shear at each of the 4 nodes, right, or out of plane displacement. And then we have rotations or moments that are acting here as well. And so that moment, the 6th degree of freedom there, actually causes a bending that would result in, let me see, put my thumb that way, that would actually cause a bending that would result in out of plane deformations. And so that's not admissible for a plane element, a plane stress element, but for a plate element, it is admissible. So when you look at a plate element like this, we end up with 1, 2, 3 degrees of freedom at each of the 4 nodes. So we have 12 degrees of freedom total. One thing that's missing from that plate element, though, it's a drilling degree of freedom. And so if you look over here on this left, now this is a membrane element that has a drilling degree of freedom. And so we refer to that as such because the rotation of this would tend to cause drilling down through the element. So when somebody says a drilling degree of freedom, it's unambiguous, right? It always means the same thing. So this is a membrane element because it has in-plane tension compression. It has a drilling degree of freedom in each node, but it lacks the in-plane bending deformations that are present in the plate element. So far, neither the plate element nor the membrane element give us all of the characteristics that we need to model floor slabs and bridge elements and bridge decks and things like that. So what we ultimately need, I'll skip this slide. This shows output for the plane stress element on the left, output for the plate element on the right, where you can see we have in-plane shears and then bending moments that exist there as well. If we look at a shell element, that combines basically the best of the plane element and the plate element for the applications that we're going to see in civil and architectural engineering structures. So we have in-plane deformations, we have bending moments in plane, we have an out-of-plane translation at each of these nodes as well. So you can see each node here has 5 degrees of freedom because this particular element lacks the drilling degree of freedom. When it comes to modeling things like bridge decks and floor slabs, we don't need that drilling degree of freedom very bad because we don't often have to worry about applying a concentrated moment in the plane of the deck at any one point. We do have to apply in-plane rotation sometimes, but there's a workaround for that. So these are the degrees of freedom you would see with a conventional shell element. Occasionally, you'll see a shell element formulation that has that drilling degree of freedom as well. but by and large, you don't have that. And the reason to omit that is you don't need it, and it makes the element a lot more computationally efficient. When you start adding these continuum elements, there's extra hoops that you have to jump through in order to get them to work in the analysis. And those hoops can be costly in terms of computational efficiency. Number one, you need a lot of them. So you use a lot of automatic meshing. So you wouldn't want to have an element that has dimensions of 24 feet by 32 feet, for example. You would want to break that down into a bunch of elements that are 6 inches by 6 inches. So there's a ton of those elements there. So that increases the computational cost. And then second, there's not really a direct formulation for the stiffness matrix associated with a continuum element either. You have to go through a process called numerical integration in order to go from the geometry of the element to the stiffness matrix for that element. And that integration process is costly from a computational point of view. Before we get to that, though, I want to point out that we have solid elements as well, three-dimensional elements as well. And most of the time, we're going to use an 8-node quadrilateral element that's shown like this, 8-node solid element, brick element, sorry, not quadrilateral. And so typically these elements have 3 translational degrees of freedom in each of the nodes. They don't often have any rotational degrees of freedom. So when you model things with a brick element or a solid element, in order to handle rotations, they have to be accommodated by using a coupled system. So you have 2 forces acting at a distance, and those 2 forces create a moment. Correspondingly, you have 2 displacements acting over a distance. You take those 2 displacements, you can figure out what the rotation relative to those 2 nodes are, and that's how you handle rotations and moments when you have a continuum model made out of brick elements. All right, so here's some applications for our continuum elements. I've been using these already quite a bit. So floor systems, wall systems, bridge decks, to a lesser extent, curved shells such as tanks and domes, and then other detailed models. So here's one example that we use a lot. This is a screenshot from the program Abacus. And some years ago, we were working with some plates in our laboratory where we were actually looking at the ductility of holes that were punched. And so, Joe, it's not dissimilar to what we're doing now, except these were punched holes instead of the flame cut holes. And so we had a student come in and do some modeling in Abacus. And what we did was we tried to capture the fracture that existed in the model. We tried to capture the fracture that existed in our experiments with the finite element model. And so you can see the experiment on the left and a loosely correlated model over here on the right, and you get some fracture that's in the model and then some fracture that's in the experiment as well. So that's a good application for a continuum element. That would be a plain stress element or maybe a brick element as well. Here's another example. This is a model of the approach spans for the bridge over the Ohio River over near River Bend Auditorium. What's the name of that bridge? The name's escaping me right now. I don't have it written down here anywhere. But this is one of the approach spans. The geometry of that structure was sophisticated enough that we thought that it would be prudent to go ahead and model it as a 3-dimensional model with shell elements to represent the deck. So this is a SAP model. These elements that are here to represent the 2 main girders, one there, one there. Then we have floor beams going transverse, and then these floor beams are supporting stringers like this. And so then we have these area objects here that are meshed into shell elements, and then that represents the deck. So if you look at the same model underneath a truckload, the truck isn't shown, but there's a truck load that's applied here, a number of axles, and then you end up with that deformation. You can see the automatic meshing that has gone on in between the unloaded view here and then the loaded view there. And so you can see that these area objects that were rather large at the beginning. Let me get back here. All right, this is one area object, and then when you perform the analysis, it's automatically meshed into probably 50 or 75 shell elements, and so you get a lot of these continuum elements. Now, this particular structure was modeled again in Abacus. Let me skip this slide for a second. What we did was we conducted constructed a high resolution model in Abacus because we wanted to look at the stress concentrations around the area where the stringers framed into the floor beams. We wanted to make sure there was enough strength here in order to avoid failures like web local yielding or web local buckling and things like that. So this was a model constructed in Abacus, and here we aren't showing the elements that correspond to the bridge deck. Okay, here's another model. This one was a model that was constructed by Ryan Carlson. He did some research on looking at ductility of eye shapes with holes in the tension flange that are subjected to a bending moment. So the idea is that you apply a negative moment here, then you end up with tension in this flange. And we wanted to look and see how much moment could be accommodated. Could these still reach their plastic moment capacity, even with holes in the tension flange? And so that was a model that was put together by Ryan Carlson. Here's some work that I did at Georgia Tech. This was a beam to column connection using top and seat angles. And we wanted to examine the behavior of this joint in a high amount of resolution. So we constructed a model of it, and this goes way back to the 1990s when we did this work. And so the model isn't very densely populated, right? We only have 1, 2, 3 elements for the web, so that's a rather coarse mesh. But at the time, that was a really a high-tech thing. I think when I ran this on, a 4086 computer, it was it took like 3 days to run or something silly like that. And then we could go in and we could look at those angles and see the stress concentrations that exist at the angle when that connected leg starts to bend. And then you see these concentrations here. And then ultimately, if we were doing it nowadays, we would want to capture some fracture at that location, but fracture wasn't a possibility back then. All right, so I mentioned that the formulation of the stiffness matrix for these continuum elements is computationally expensive. And the reason why is that they don't have a closed form solution for the stiffness matrix. When you go in and model a frame element or a beam element or a truss element, you just have a 4x4 or a 6x6 stiffness matrix that you can substitute values into, E, I, L, cosine, sine. And so that's relatively straightforward, even using a package like Excel. But when you look at a continuum element like this that could have geometries that are widely varying, you could have a quadrilateral element, for example, that is nice and well behaved that looks like that, but you could also have a quadrilateral element that looks like that. And so it's not possible, it's not convenient anyways, to have a closed form solution. Instead, what you do is you define something called a shape function that defines the variation of the independent parameters across the dimensions of your element. So if we're looking at a plane stress element, for example, what we would do is define the stress or the strain relationship as you move from one node to another. So the stress might vary as you move in this one direction. It might also vary as you move in this two direction. And so what we have is a function based on the shape of the element that gives us the stress as we move from one node to another node, or move from one point to another point within that particular element. These are called shape functions. We typically use lower order polynomials for those. Sometimes we assume that the stress is constant from over the entirety of an element. If we have something more sophisticated, we might use a linear stress element where the stress varies linearly over the area of the element. In some cases, you can go to higher order polynomials where you might have a quadratic shape function instead. I'm sure that if you ask Dr. Rosati, he teaches the 7013 class or 7012 class where they talk about finite element modeling in Abacus. He has a much more elegant definition of these than I do. So if we look at the triangular elements, they're usually a constant strain triangle or a linear strain triangle. In order to define a linear strain triangle, you need 3 additional nodes. So you have 3 that are defined here. You would also have mid-face nodes that are defined like that. And then with that extra displacement, then you can define linear strain variation over the face as well. When you look at quadrilaterals, you can have constant strain, or you can have a situation where you have extra nodes defined on two faces. That would be 6-node Q6. You could have a case where you have nodes defined on all four faces. That would be a Q8. And you can even have another variation where you have a node at the center of the element, and that would be a Q9. So you have 9 nodes defined. And the more nodes you have, the higher order the shape function can be, and you can get more accuracy with a lower number of elements in your model. But the more nodes that you have in an element, it adds to the complexity associated with generating the stiffness associated with that element. So it comes at some computational cost. So there's there's a cost benefit ratio. You have fewer elements that are higher order, then you save computation by having fewer elements, but you have extra computational costs by having a higher order shape function. On the other hand, you can have a larger number of elements that are a lower order. You add costs because you have more elements, but you save costs because you have a lower order shape function instead. So the stresses in these elements are computed exactly at certain points within the elements. These points are called integration points, and we numerically integrate the shape functions in order to get the stiffnesses. And so the process that almost every package uses is a process called Gauss quadrature. And you guys might have learned this back in calculus. My guess is that if you did, they probably spent 15 minutes talking about it, because I don't think the mathematicians really use it that much. But it's a very convenient way of numerically integrating in order to go from the element definition to the stiffness associated with that element. So Gauss quadrature is typically used. And because of that, when you look at the integration points, they're often referred to as the Gauss points within an element. And so when you go and look at the output from a quadrilateral stress element or a triangular stress element, they'll usually report the stresses at the Gauss points or at the integration points. So you can have reduced integration formulas that reduce the amount of integration that's required, 1 integration point instead of 4 integration points. But then when you use those, you end up with some side effects to the reducing the number of integration points. And one of them is shear locking. You can also end up with hourglassing problems as well. And this is a deformed shape that is indicative of that hourglassing. And so what you see is these elements tend to deform like that, and that is a problem with the formulation of the element. So if you end up with a model that looks like that, then you either need to go with an element that doesn't use reduced integration formulations, or you use a finer mesh of the same, using the same elements. And often when you go with a finer mesh, you can get away from that hourglassing or that shear locking. All right, the shape of a plane element matters as well. Generally, what you want to have is an element, if you're using a quadrilateral element, one that looks like a square or a rectangle. You get more accuracy, better results out of that element than you do if you have one that has goofy sides on it. So what you want to see are elements that look like this, maybe an element that looks like that. What you don't want to see is an element that looks like this, right? Yes, that is a quadrilateral, but when you start using the lower order polynomials to approximate the shape function for that, then you end up with a lot of error in that particular geometry definition. So the aspect ratio also matters. Yes, this is ideal. This is usually okay, but if you have a quadrilateral like that, then that's usually not okay. What you would want to do is break that up into a number of sub-elements. So you'd be better off using 4 elements that are approximately square than you would be using 1 element that is really oblong. All right, the mesh density also matters. And so what's shown on this slide here are 4 different mesh densities associated with the same model. Let me provide a little bit of context here. I'm going to go back to a slide that we showed earlier in the presentation. I got to find it. Here it is. So this particular slide shows a model of a plate with a hole in it. And so what we were doing is applying a tensile stress up here like this, same thing down here at the bottom. and we were looking at the behavior of this plate with that hole in it and looking at the stress concentrations. So we talked about the idea of axes of symmetry or planes of symmetry when we were talking about joint constraint definitions. And so one of the things that was done was you can actually model 1/4 of this physical structure. And so you have an axis of symmetry here that can be taken advantage of. You have an axis of symmetry there that can be taken advantage of. So you can model just that part of the physical structure, and you can cut the size of your model by a factor of 4, which will save a whole lot of time in the analysis. So going back now to slide number 28, you can see here that there's several different mesh densities that were used in the definition of that model. This one over here on the left is rather coarse. The one over here on the right is rather fine. And so what you want to do is you want to have a mesh that is sufficiently fine so that you get accurate results, but you don't want a mesh that's too fine so as to lead to longer run times than you really need. So generally what you'll do is conduct a mesh sensitivity study when you're doing something like this, where you'll start off with this guy over here. You'll conduct an analysis and then look at the output. Maybe you're looking at the stress that you get there. Maybe you're looking at the amount of displacement you get out of that node. Then you would come back in and you would increase the mesh density. Usually there's a seed number, a seed size that you would put in there that's an indication of how dense you want the mesh to be. You would again look at those results, and maybe they change by a fair amount going from model 1 to model 2. And so you keep modeling it with an increasing density until the results that you get are about the same from one model to the other. And that mesh sensitivity study then will tell you how dense the mesh has to be in order to get results that you need without being too dense so that you use computer time that you don't need. All right, and you also have to be careful when you vary the density of a mesh. If we go back and look at this slide, they use triangular elements everywhere. I don't see any quadrilateral elements in these. So the triangular elements are nice because you can fit in odd shapes with triangles, and it usually does a good job of matching up the nodes. But remember that there are nodes at every corner of these triangles. And when you look at the way this is connected, the only place that one element is connected to another element is at the nodes. And so if we go in and look at this, for example, there are nodes associated with these bricks, right, like that, and there's nodes down here too, but this element here isn't attached to the element below. This element here isn't attached to the element above. And so if we come in and apply a load to the top of this, you end up with an overlapping of these two edges because those nodes aren't on both elements on both sides. So there's a couple of ways you can accommodate that. One is you can accommodate it using a transition mesh. The other is to use an edge constraint. So here is a transition mesh where we've gone in and used triangular elements in order to accommodate the difference in the geometry. Here we use 1, 2, 3 triangles and 2 quadrilaterals. And so again, at every point, these elements are meeting at a node. The alternative to that is to come on and use an edge constraint. And an edge constraint is where you go in and use the joint constraint and you say, I want all of the joints on this particular line to behave as though they are on an edge. And then when you do that, then you can have mismatched meshes like this. That's hard to say. Mismatched meshes, and the joint constraint will take care of the mathematics automatically for you. All right, so I'm out of time. This is a good place to stop anyway. So I'll go ahead and discontinue here for today. I'll jump back online at 2:30 for my office hours. And then next Tuesday, when we get back together, I'll pick up here with this presentation, and then we'll work our way back over to SAP 2000, where we'll add some shell elements to our model of the Tower of Terror, and then I'll show you how they can be used to model the floor slabs. All right, any questions before we wrap up? All right, then I'll hang around for a minute or two to make sure if somebody has something they don't want to ask in front of everybody else. Otherwise, I'll see you guys either at 2:30 or I'll see you next Tuesday in class at 12:30.